Billet Titanium connecting rods for our 4,000 horsepower Hell engine. Well, we finally have these done. We initially tried to get these done from basically every aftermarket connecting rod manufacturer, including like some really high-end ones. We actually managed to get one single quote, but that was 4,000 euros per connecting rod. So at 6 connecting rods, that's not going to make a cost-effective engine, unfortunately. And all the other manufacturers, actually some of them were very interested and said they could do it. Then we sent the specs over and they were like, yeah, and ghosted us. So yeah, anyway, here we are now with our own connecting rod design, and it ended up wasting a huge amount of time going through all of that. But yeah, now we've figured out the stuff, how to make these, what to take into consideration, the suppliers for the bushings and all of that. But also an awesome opportunity to yeah, look at these with you guys and explain what goes into one of these connecting rod designs. So first of all, the overall shape and design is very dictated by the engine packaging. So the top end is dictated, in our case, by the piston. So this is extremely tight around the piston shape, so it just barely fits, and there's just barely enough space to be able to rock the connecting rod without hitting the stiffening ribs on the piston. The shape here is very, very close to the bottom of the cylinder bore without touching it. So this is basically limited also. And the bottom part here has a nice sort of V shape. This is so that it clears the bottom of the, so we don't really have an oil pan in the engine because it's a dry sump system, but like the bottom of the crankcase surface there is angled so that we get the oil on the surface to flow in toward the central ducting suction area. So that's angled. So that's why this surface is also angled to just barely fit in there. And that gives us some restraints on what we can do, like internally, how big it can be externally. And yeah, the piston pins, of course. So the piston pin, that's dictated by the piston manufacturer, like looked at our specs and we're like, okay, well, we can maybe make it work with this size of piston pin. So that's what we have on that. On the bottom end bearing size, this is massively larger than what we would want to run, really. But with the crankshaft, so this is a 60-degree V6 even fire engine. And that unfortunately means that the crankshaft is very, very flexible because you have so much space in between all the bearing surfaces, and you need all the space between the bearing surfaces to be able to distribute the loads on the crankshaft so that you don't have these massive stress spikes in small radius corners and stuff like that. So that ends up giving a very narrow connecting rod, unfortunately. And with a very narrow connecting rod and a very large diameter, that means we need custom bearings because there's nothing off the shelf that we could use for it. So we have custom race bearings coming for it, and we have custom small end bushings also coming relatively soon, arriving. So yeah, custom everything basically. But let's look at some of the details here on the design. So the small end, as I mentioned, is very, very close to get to just clear the piston and get the motion range that we need from the engine geometry. So that dictates these shapes, and that unfortunately rules out using aluminum connecting rods. Aluminum just has a too low modulus of elasticity, so it would require a much beefier cross-section area here, and that just won't fit in the piston. So we can't use aluminum, so we have to use either titanium or iron, steel, which are basically the other two options then. And we still want to use the most flexible material possible because with the piston pin situation, so we have extremely high cylinder pressure design target on the engine, and that basically means that at maximum cylinder pressure, pressing down on the piston pin is basically a banana shape. So then we need to get this like straight bored hole through the connecting rod, like work in a banana shape. So that of course means that it needs to flex like the piston pin also. So that's why we have these very intricate detailed shapes here around the small end. This is like very heavily optimized to get it to flex correctly and to not have like any sort of stress peaks in the shape here, and how it's distributed towards this cross-section area here. So we're also cross-section limited. So there are all kinds of different forces here. So we have compressive forces, bending forces, and some of them are fatigue type forces and some of them are not fatigue type forces. So with the compressive forces, for instance, those will not cause fatigue typically unless you have buckling issues. But in this case, yeah, we can make the design so that we're not buckling limited. But anyway, the cross-section area here is limited by the compressive forces. So that's locked in, but we need to maintain that cross-section area up to the piston pin. So that's why these stiffeners like widen, but also it gets narrower so that we can flex it correctly. And this is like, yeah, so much work to get done and get the CAD stuff set up so that's also manufacturable in some reasonable way. But anyway, then when we get the forces and move downwards here towards the big end actually is quite a bit of a problem with this really big diameter that is required from the crankshaft point of view. From the connecting rod point of view, you want as small of a bearing as possible. That just makes the geometry much stiffer and much easier to design overall. Yeah, we need the bigger bearing to make it work. So that means there are all kinds of design considerations. So we really need a relatively thick surface around here to get enough stiffness, because we need the geometry to stay as round as possible, especially during valve overlap and at high RPM, also on the sort of sideways forces when the crankshaft is pulling the big end sideways. You get from inertial loading these like banana type shapes and these all kinds of flexural loads in these this big end, and especially around the split face. So that's also why we have a tooth interface here to have positive locking, not just rely on the friction from the bolt clamp. And yeah, the bolt clamp also. So yeah, these are M9 ARP 625 plus material bolts. These are basically I think the highest loading bolts ARP has off the shelf. We can get custom ones done, of course, also if required, but these are just barely good enough to be able to get the loads we need for this connecting rod. So very happy about being able to use some off-the-shelf components at least. And yeah, we optimized the tightening torque on these to get the correct stretch. So we double checked all of that and did some calibrations. That works well now. Then to keep the bottom half here stiff, we have this type of I-beam set up so we can reduce the material as much as possible in like the neutral axis where there's not much loading. Then we have extra material on the outside and on the inside so that we get as much like stiffness in like this type of a wobbly bending movement as much as possible, to keep like the bearing pinch as low as possible during valve overlap, which is a massive issue at a very high RPM, which is one of the situations where aluminum rods are really good, because you can just run very, very thick wall thicknesses and they just like have a very, very good stiffness from the geometry then. But yeah, we did this to reduce extra weight here. And these shapes here are to reduce weight, but also to distribute the load more evenly from the compressive force evenly over the whole bearing surface here. So we have compressive forces that is distributed towards the center and towards the outside, and we have again some lightening parts here, but not too close to the threads to fatigue those too quickly. So there's a lot of design stuff that goes into one of these connecting rods ultimately. Finally here, series producing these now for our engines, and can't wait to put these together.